Calculus, Lesson 8.3, Part 2. We're going to learn the disk method today. So the neat thing about the disk method is basically it's cross sections, but they're circular cross sections. So if you have a function, like this one would just be a straight line constant up here and a constant down here. And then if you take those and spin around the x-axis, you get a circle. So that's called the disk method, like a CD, like a disk. You're getting a whole bunch of circles and you're going to integrate them across, and that will give you your volume. This one here is vertical, so you can also do this with respect to the y-axis. So if I had a function defined in y that basically did like the side line of this, and then I spun it around the y-axis, I would get this shape. Think of it as being solid for the disk method. I don't know. I guess the bottle is another good example. You'd have to have a function that defined this, but that would just be a constant. And then we got a little bit of a line here. So this one would be pretty easy to do in two pieces. Just add those up. But the idea is you got to picture them rotating around. So these are like 3D model pictures of what we are creating from little functions. So for example, if I have this little wave as my function and I spin it around, I'm going to get a cone, sort of like a plunger shape here. To find the volume of that, I can take all of the disks, the big one all the way down to the little one, stack them up, add them up, and I get my volume. So as these get thinner and thinner and thinner, then I'll get a smoother and smoother curve, and I will get closer and closer to the actual volume of the 3D solid. So you can do this, like I said, with respect to the x-axis. So this one here, my rectangle has a height of whatever the function is, and then and that would actually be the radius of the circle, because I'm going to spin it in the x direction. And since that's the radius, it would be r squared. If I basically, that would be like a half of a ball, a semi-sphere. This one, if I spin it this way, I would get the same shape, but it just maybe would be easier to define that function in terms of y. So this one, the height, turn your head sideways, the height is the function, and the width is your delta x or your delta y, and that's why this has to be written here, because it is your width that you're changing smaller and smaller and smaller, so that we can add those up and do the integral. So for our first example, the first thing we need to do is have a picture of what we're doing. So we have the region of the graph, 2 plus x cosine x. So you might not know what that looks like. You might want to take a graph of it. And the x-axis over the interval from -2 to 2. So what does that look like? Well, from -2 to 2 means I'm going to look from here to here. We have the graph of 2 plus x cosine x. That's this graph here. And I'm going to take the region between that and the x-axis, and we are going to revolve it about the x-axis to generate a solid. So this little sliver right here is going to spin around and make a disk right here. And then all of these are spinning and spinning and spinning and spinning. And to give you a little bit of better picture, you can take what you've got there and kind of mirror it down here. And you're actually going to get, if you turn your head sideways, it kind of looks like a vase. All right, how do we find the volume of that then? Well, we're going to take the integral of, we're going to integrate from -2 to 2, if you haven't figured that out yet. They actually gave me that interval up here. And for this little sliver right here, what is its height? This would be the radius of my circle. And these are circles, right? Circles, pi r squared. Okay, what is my radius? My radius is the height of this, which is the height at that function. So my radius is 2 plus x cosine x. That's it. And then we just put this into pi r squared. Since I'm using x, 2 plus x cosine x. And then the width of this little rectangle is dx. That's all we have to do. If we calculate that from -2 to 2, we will have the answer. So for these problems, definitely going to probably use a calculator because we've got the product rule in there, and that would not be very fun to do by hand. So put it in your calculator, and the answer is 52.43 cubic units. It doesn't have units, but if it had units, they would be cubed. All right, so this is another, just a kind of a, I got it from a different place so that we'd have some more examples, but basically you take the curve, you spin it around. This is just another 3D model of what you would get. If you have the equation of that, that one looks like a parabola, pretty simple. You would just take that function, f of x, whatever it is, if it's a parabola or whatever, and do pi that function squared, because that function is your radius that you're spinning it around, dx, and then your interval from a to b. So it's, once you get your function there and you know that's your height, the disk method is not too bad because your function is your radius. So here's a specific example. This one's drawn out for you. There's the equation of the curve, and there's a nice little picture of the disk that we're going to make there. So my suggestion is pause the video and see if you can solve this problem. See if you get the same answer. All right, since this one was pretty easy, I've just got the answer up here. We're going to integrate from 0 to 5, pi r squared, where r is my function up here that I've already got. That's it. That's the problem to do. Now, they did this one out by hand because the math was not super hard to integrate. And the answer has pi in it. If you multiplied it out, that's fine. One note, when you're doing this by hand, it makes it a lot easier if you pull constants out. So pull the pi out and just integrate the radius squared. There we go. 83.3 pi units cubed. Just a note, you can also do this along the y-axis. So this parabola, instead of spinning it in a up and down around the x-axis direction, I can spin it around the y direction. In order to do that, you just need to make sure that your equation is in terms of y, not x. So this is y equals x squared. In order to integrate it the other one way, I would want x equals plus or minus the square root of y. So that's going to be the equation I use. So if that's my radius, when I go to integrate it, I'm going to do pi r squared, and my r is the square root of y. Well, the square root of y squared is just y. Since we're spinning it around, you don't really need the plus or minus. So that's what's going on there. So this is where the pi y, that's why you're not seeing the squared, because we had the square root and then we squared it. And then we would integrate that from 0 to 4 because we're doing it in the y direction, so up and down here. Don't forget to put dy, so watch out for those variables. Keep the right units. And the answer's down there if you want to finish that problem. Another thing that can happen on these is they might not swivel or spin around the x-axis or the y-axis. They might shift over and spin over a line. So in order to do that, what you just need to do is shift your graph. Basically shift all these points back to the y-axis, or if it's a horizontal, shift it down to the y-axis. So this equation here is y to the 1/3, well, it's x cubed, so that means it's the cubed root of y, which is y to the 1/3. So that's the name of this in terms of y, because we're spinning it in the y direction. And then if I want to scoot it over 1, that's where this 1 minus my graph comes from. I'm just going to take 1 and subtract those all over there and then spin them around. And so that's the function that I'm going to spin. So when they're shifted over, think about this like transformations that you learned way back in Algebra 2. Shift it over, and then that is your new radius. And that's the end of the lesson on disks.